Hello, everyone. Today, we are going to discuss table chemical data, molecular file formats, and some chemical databases, and also some principles for data storage, as well as we are going to discuss a Jupyter notebook that the notebook is related to the last two lectures, and you will see how exactly. So if we want to consider data in chemistry, we may ask ourselves about what data it is. And some data is spectral data. For example, we can have a mass spectrum like this one. So it can be other spectral data, or data collected with nuclear magnetic resonance spectroscopy or any other spectroscopy method. We also can encounter, and we do encounter quite often, table data that is related to experimental conditions. For example, here we have a chemical reaction that proceeds only with an added catalyst, and this table below summarizes experimental data on different conditions, different catalysts, and different additives. So we should be able to store this data, and the natural way to do this is using electronic tables. So we also can store computational data, like the data that was obtained via quantum chemical computations, and using electronic tables. So it's a natural way. If we if you want to store and process spectral data, electronic tables are obviously maybe a convenient choice as well, because if we consider every peak on the spectrum, this is a collection of coordinates on the vertical and the horizontal axis. So if we need to store and process table data, there are two obvious choices. These are concise formats. First of all, we should mention the CSV format. So CSV is an abbreviation for comma-separated values. So we simply store entries that are separated by commas. We can store strings, string data, and we can store numbers as well. Here we should note that for floating point numbers in literature, so we use points and not commas. like in Russian literature. So this makes no problem, obviously. We can also use tabs as separators for data, and in such a way we have the TSV format. So we simply separate data by tabs, and we also can store numerical and string data. Of course, these two formats are simple and don't allow us format data for convenience. And of course, we can use MS Excel electronic tables. This format gives us rich formatting, including different fonts. It allows us using bold fonts like this, or italic fonts. And also we have MS Excel tools for data analysis, processing, etc. And here I must say that no one should underestimate MS Excel. In fact, its features are really outstanding. And if we process small data, MS Excel can be a convenient choice. For technical details, I provide you a link on the format specifications. And here I encourage you to tinker with the Xlsx format. So let's tinker a little bit. Here I have a demo Xlsx file. It contains data obtained with quantum chemical computations from my previous work. And so it's formatted. And what we can do, we can unpack the file. On my computer, I use the Kika program as a tool for compressing and extracting data. And we can unpack our Xlsx file as an archive and open it. So if we open it in a text editor, we will see that the folder basically contains XML files. I can browse via the folders, and we will see these files of this type in most folders. So we can open it in a text editor. So this is basically a collection of XML files. And here I should, of course, mention what XML is. So XML is an abbreviation. It stands for Extensible Markup Language, and basically this format allows storing data in a structured way. Later, I will show you that the format basically gives us unlimited formatting options, and it also supports Unicode, so you can use some complex symbols like Cyrillic or Greek letters. So and speaking about the XML format, I should also say that it's the basis for a great number of markup languages. So every markup language allows us to structure and store data in structured and formatted way. And if we browse through the list of XML-based languages, we see that, well, the list is very long. And it exhibits markup languages for many different applications. It may be some web applications or research applications. So the list is huge. And it's also human readable. We will discuss some simple XML files later, and it can be used to store research data as well. So let's consider an example. So basically, XML organizes data by using the so-called XML tags, like this one. Tags can have attributes, and every XML files can have comments like this one. So a comment tag begins with an exclamation sign. Here we have a comment. So basically, this XML file is a structured representation of a recipe for bread. You can find a copy of this file in the supporting materials I've sent you recently. And also we can store spectral data, for example, like this. So XML is a format for storing mass spectral data. You see that basically it's a huge file. You can find this file in the supporting materials as well. Also, you can easily Google some conventions that must be followed during the construction of an XML file. And so also I provide you a link on a textbook in Russian. Next, we should discuss the JSON format. So it stands for JavaScript object notation, and it's a human-readable format as well. We will see an example a little bit later. And the format allows us to store different data structures like objects, arrays, values, etc. The JSON format is used in research as well. So it can be used, for example, to store parameters of nuclear magnetic resonance experiments, like in this file. So, and considering this file, you can find a resemblance with Python dictionaries. So this format can store Python dictionaries as well. Of course, pandas data frames are a convenient format for storing for storing table data. And we discussed pandas data frames in our second lesson. So we generated pandas data frames, processed them, and analyzed data that was stored in example data frames. So you can revise the Jupyter notebook I provided you with. So we have discussed the main table data formats, some of which we are going to use later in our workshops and demonstrations. And now we should discuss data formats that are commonly used to store molecular structures. So if we aim to design chemical compounds, we should have some format for storage of molecular structure. The SMILES format is probably the simplest format to store such data, this data. And it was developed 3 decades ago. It's also an abbreviation, so it stands for Simplified Molecular Input Line Entry System. And indeed, it stores molecular structure as lines in line format. So I provide you with several links on the that give you description of the format, features, and some examples. So we can encode quite complex molecules by using this format, and we can follow even a link on Wikipedia. So basically, it allows us to describe, to encode different elements and even different isotopes. Bonds are encoded with these symbols. So, for example, we can encode double bonds with this symbol and triple bonds with hashtag. There are some examples. We can encode ring structures as well. So we should use numbers to assign atoms that are connected in a ring. So basically, a SMILES string represents includes path from which we can have secondary carbon carbon path. So we in such a way we encode a tree-like structure, and by assigning numbers, we connect these atoms. So if we want to encode a structure of ciprofloxacin, which is a widely used antibiotic, we should use this number, this string. So you can have, by following the link, you can have the formal description, and I should also mention that SMILES and its extensions give us really give us rich formatting options. For example, we can encode stereo isomers by using isomeric SMILES. So I've told you about isotopes. We can differentiate cis and trans isomers, and we can even encode inorganic molecules that represent trigonal bipyramidal or octahedral geometries. So there are several conventions that should be followed if we use SMILES. And please note that if we, in a SMILES stream, we usually omit hydrogens for simplicity and brevity. In fact, we can include hydrogens for some specific purposes. If, for example, if you want to describe 3D structure precisely, however, natively, usually hydrogens are omitted. We are going to generate and process SMILES strings later by using the Pybel library that is an interface to OpenBabel that I've told you about in the previous lesson. So the SMILES format is widely supported by chemical software, and there is an online editor that you can access by following the link I provided you. So on this site, you can write some SMILES strings and analyze them. Let me show you. So if we have CCC, we have a propane molecule. We can propagate the chain, or we can introduce a cycle. Let me reload the page. Here. And we etc. We can introduce some heteroatom functional groups, like, for example, we can do it this way. And so this note that the site parses the SMILE string I'm inputting, and if the string is invalid, it gives me an error. So you can introduce a side chain by using parentheses, and we can do something like this. So O is stands for oxygen simply, and the editor adds a hydrogen atom automatically, and we can do that. So going back to SMILES, I should also mention that we can encode the structure of ionic compounds like this by using a dot, and we can encode atomic charges by using plus or this sign. So please note that this not a dash. So the SMILES format is simple and human readable. For example, by considering such a molecule, so it's a melatonin molecule, we can find cycles, and I've colored cycles in this molecule for you. Compare it. We are going to use SMILES, and because of its simplicity. However, I should also mention the InChl format that allows you to encode quite a lot, like tautomerism, isotopic composition, etc. And the problem with InChl that it's hardly readable by human. So the same melatonin molecule is encoded with InChl in this way. And well, it's much difficult to read this string. The format was developed by EOPAC and NIST. I provide you with the link on the original publication that describes the format and aims of the developers, their motivations, so, and give some examples. Here we discussed two formats that encode molecular graph. So basically, we have, in most cases, we have a direct correspondence between molecular formula and SMILES string. The same is true for InChl. However, we are going to need several formats that are commonly used to encode molecular structure in 3 dimensions. So the simplest format is XYZ. So files of this format have an extension .xyz, and this is also a concise format that stores only Cartesian atomic coordinates. Here, I give you an example of XYZ file and a visualization of the molecule that is encoded. So it basically it's cisplatin. Here we have the platinum atom, 2 chlorines, and nitrogen atoms and hydrogen atoms as well. The file has block structure. The first line is the number of lines in the file. The second line may be left blank. However, it can also store some comments related to the molecule, and I'll show you some XYZ files that has comments in the second line. Next lines give us elements and atoms and Cartesian coordinates. This format is easily processed with OpenBabel, and despite its simplicity, it can serve several important. It can help us to solve several important problems. So if you want to store molecular dynamics trajectories, we can use this format, and we have generated some molecular dynamics trajectories in the previous lesson. We can also visualize atomic vibrations by using this format. So let's consider examples. First of all, here I have a molecular dynamics trajectory that I've generated during my research, and I can open it with JML. Here we have an anion copper 5. These are copper atoms, and these are chlorines. So it's an anion copper 5, chlorine 6. And we should set frames per second, and we can analyze, see that trajectory. So we here we have molecular motion, and this is basically a molecular dynamics trajectory that describes time evolution of an isolated ion. Let's see this text file. Let's have a close look. As I've told you, the second line can store some comments, and indeed here we have data on energy, on the total energy and the gradient and gradient values. After the first frame, so here we have second and etc. So basically, we have visualized the time evolution of this molecule under some conditions that were defined by simulation parameters, and by using the XYZ format, we store this in a more or less concise way that is human readable. We can also simulate molecular vibrations that can correspond to vibrations that are caused by absorption of photons in the infrared region. And this is a file that also that stores such a visualization. So again, we have comments and numbers of atoms. Let's see what we can do with this. So basically, indeed, each of these files contains visualizations of atomic vibrations. And the problem with this format may be that This is a very concise format that gives us no info on the chemical bonding. Of course, this may be a feature for some applications. However, if you want to store data on chemical bonding, we should use other formats, like, for example, mol files. This format gives us info on molecular charge, connectivity of atoms, and even bond types. You can follow the link for a brief description of the format, or you can use this book that gives info on most common formats for the storage of molecular structure. So every MDL mol file has block structure in which we have atomic Cartesian coordinates, element symbols, and data on atom connectivity. Also, here you can have data on atomic charges, as I've told you before. And let's use OpenBabel to generate a mol file from an XYZ file. Here we have several files, and also we have an XYZ file. Let's see what we've got here. So it's the same cisplatin. Let's convert it. So the molecule is converted successfully, and we can open this file that gives that contains the same molecular structure. And here we have a mol file that stores all this data. By the way, you should note that OpenBabel generates atom connectivity automatically by using its encoded features. Of course, if we consider some complex molecules with complex chemical bonds and complex functional groups, some unusual bonding motifs, OpenBabel may fail in generating correct atom connectivity. So please note this. However, for organic molecules, usually it works perfectly. We should also discuss this third format for that encodes 3D structure of molecules and crystals. It's PDB, so this abbreviation stands for Protein Data Bank. PDB files that have the .pdb extension were developed to encode macromolecular structures, for example, structures of proteins that were determined by X-ray diffraction. So the format has, PDB files has format block structure that have many types of records. A typical PDB file looks like this. So it has header and some titles. You can follow the link on Wikipedia for the description of the format. And also there is a specification of the record types. Note, for example, that there are some lines that contain data on atoms of the protein, and that's the part that are parts of the main chain, and there are heteroatoms as well. I should also mention that every one of these formats can easily be processed with OpenBabel. And for those of you who use Linux and Windows operating systems, I would like to suggest using the GUI version of OpenBabel, so you can install it, and it allows you to easily convert files, so you immediately have the output. And you can also use some optional, you can customize conversion by using some options. So PDB files can also be processed with OpenBabel, and we are going to generate some some PDB files with Avogadro to get familiar with the format. So let's import some crystal structures. As an example, let's consider graphite. And here we have crystal cell. We can build a supercell by repeating it. So let it be 5xx5. And basically we have a double layer graphene here that, due to periodicity, represents an ideal graphite crystal. note that here we have data on the crystal cell. So we have cell matrix, and we have Cartesian coordinates of atoms. So let's save this crystal. Using the PDB format. So it's the same file. That includes information on the cell parameter, crystal cell parameters here, and as long as since we model, since we represent non-protein structure, so all lines are heteroatoms. There are data on atom connectivity, etc. We can also build a supercell of some other crystals. Let it be something really interesting. For example, InChl. To build a supercell. And here we have a periodic structure that is layered. And here I would like to ask you, do you know what InChl is? That essentially contains yttrium, barium, copper, and oxygen. Are there materials chemists?
Maybe it's perovskite, super conductor.
Yes.
Superconductor.
Yes, it's an example of the well-known superconductors. Yes, InChl is a high-temperature superconductor, and if we speak about high-temperature superconductivity, you should know that high temperature means that the phase transition temperature is about the temperature of liquid nitrogen. So it's really cool. However, yes, it's a high temperature superconductor. You can generate several crystals and save them in the PDB format. However, I should warn you that Avogadro sometimes can generate atom duplicates on the same position in the Cartesian space. So if you parse such a file, I should warn you that you should look for possible duplicates, and in fact, there are some. So you can. I suggest you further practice later. And for now, I would like to mention several chemical databases. First of all, I would like to mention public chemical databases because here I have a list that is a selection from this article. You can follow you can look this reference for the complete list, and I suggest you looking at several databases for a simple reason. If you are going to do any machine learning, you will need obviously you will need data. And for now, there are many public databases that can be accessed for free. So, for example, Zinc is often used in machine learning studies of biologically active molecules. Materials Project is a huge database that includes data on materials. The data was obtained by quantum chemical computations. So here we have computationally obtained data. And the next slide gives you, there is a list of links on chemical databases with experimental data. So, for example, here we have, for example, the famous PubChem or NIST chemistry webbook. Some databases are more convenient to use in machine learning studies than others. So, for example, it's most convenient to work with computational databases, most of which were constructed for machine learning purposes intentionally. So I suggest you following links. And also here I should mention two proprietary databases that store enormous amounts of data. First of all, I should mention Xlsx, that is maintained by Elsevier, and it stores millions of entries, info on millions of organic reactions and compounds, and it's an expert curated database. And I should say that they try to make it as better as possible. So indeed, expert curation is well, it's necessary, and I'll show you later why. And I should also mention SciFinder, that is provided by the CAS. Of course, there is a obvious problem that these are proprietary databases, and usually our institutions and universities have access to these databases, but I cannot guarantee, so it differs from an institution to institution. And I should also mention that you cannot easily gain access via an API to these two databases. So you have to ask for permission by the publisher, and it can be hard to obtain it. So why database curation is key? Databases that store experimental data may have some issues with missing data. For example, if we are going to compile data for the rational design of reactions, we need data on reaction conditions, and on later in further lessons, I will show you why data on reaction conditions is truly important. So there are missing data on reagents, or some entries may even miss reaction products. So ongoing database curation is really important, and there are some problems. There are also some problems related to reagents that can be listed as reactant substances and in reaction conditions, causing duplicates. And if we speak about reaction predictions, for example, we need data on we need accurate data on reaction conditions. So, for example, some database entries can have temperature assigned as, for example, room temperature. But what does it mean? Like room temperature in hot summer, this may be one temperature, and in a chilly lab in winter, it can differ by tens of degrees Celsius. Pressure varies, atmospheric pressure varies as well. So exact values can be crucial. And of course, if we want to identify compounds in databases, there may be some problems related to non-unique compound names, like using trivial names versus the naming according to the EU pack. At the end, I would like to mention the so-called FAIR guiding principles for scientific data. I suggest you reading this article in Nature. In scientific data of the Nature journals, and the paper describes principles that are suggested for storage and distribution of and structurization of research data. So data should be findable, obviously, to if you want to share it. And it should be accessible, interoperable, and reusable. Here I have detailed. Here I give detailizations of each of these principle. So you are free to ponder the guides. And now I would like to show you the Jupyter notebook that is related to the material of the last two lectures. So here, this Jupyter notebook illustrates some features of the so-called Bible I've told you about. So it's the Bible library provides functions and classes that interface OpenBabel, and you can find an online manual by Googling, or I'll send you the link a little bit later. So let's read a file. In the XYZ format. We can visualize the molecule, and you can find this file in the supplemental materials I've sent you. So we can also process SMILE strings by using Bible, like this one. We can visualize it, and we can so we have our arginine, and by using, basically here we have generated an object that stores data that stores molecular structure, and we can add hydrogens to the structure. So basically here we have structure that is electron neutral. And next we can use for example, we can use attributes like formula. So we can indicate molecular formulae, and so next we can calculate molecular weight or number of atoms. By the way, if you want to, so it's an object. And the molecule, the corresponding molecule, has 26 atoms. And let's see what we've got here. Basically, every atom has 0 Cartesian coordinates. We didn't generate any, and basically we have a dot. So let's use molecular dynamics, molecular mechanics to optimize the structure, just as we used Avogadro to perform molecular geometry optimization. So it's molecular optimization proceeds very rapidly, and we can indicate. We can see all Cartesian coordinates here. Now, obviously, our molecule is 3-dimensional, and it's electroneutral, as I've told you about. So we can do, we can process, we can generate and process huge numbers of molecules, sets of molecules automatically by using PyBel. So for example, let's generate derivatives of phenol and generate ortho, meta, and para isomers of phenol with different substituents. Let it be chlorine, CF3, methyl, amino group, carboxyl group, SH, thio group, and oxymethyl. So we can visualize molecular structure. Let it be this. Here we have the phenol with CF3 substituents, and we can visualize another generated molecule. Yep. Next, we can use PyBel, and basically we can use OpenBabel to calculate molecular properties that sometimes are used as descriptors in QSAR studies we are going to discuss in our upcoming lessons. So, for example, we can calculate the so-called log P. Log P is the octanol water partition coefficient, and basically it indicates molecular polarity. So let's calculate log P of our generated panels. By the way, note that we used SMILES to calculate log p here. We will discuss this in further lessons. I mean, which info do we need, and which methods, we will discuss methods for log p calculations and which info on molecular structure we need to calculate these molecular features. So log p varies from 2.02 to 1.4. And here I would like to show you some code on how to calculate molecular fingerprints and calculate molecular measure molecular similarity by using tenometer coefficients. There is an article on Wikipedia you can follow. Basically, we are going to calculate tenometer coefficients that sometimes are called Jacquard index, and it's calculated in a nutshell. It's a simple the formula for calculation is simple. Basically, we use the intersection of two sets, and we also compare the sets by using their intersections. So let's calculate molecular fingerprints of the FP4 type. If we briefly about molecular fingerprints, there are several families of molecular fingerprints that are supported by OpenBabel and implicitly Babel. They encode molecular structure in such a way that they show the presence of absence of some functional groups in a given molecule. So, for example, molecules can have chlorine, CF3, methyl, amino functional groups, etc. So we are going to compare the generated molecules of substituted phenols. And for this, we are going to compute the FP4 type fingerprints. You can find info on the fingerprints that are supported by OpenBabel by using the command obabel L fingerprints. So you will have the list, and there is info on every fingerprint family. So here, for example, I've opened I've kept a file on the FP for fingerprints. There is a description. So these fingerprints encode the presence of organic functional groups. There is a long description, etc., etc. And basically, so let's compute the fingerprints and compare the so-update fingerprints of two substituted funnels. And these two differ only by one functional group. So by comparing the computed fingerprints, we see that there is a difference here. So we can convert the computed fingerprints to numeric vectors, and we can save our vectorized fingerprints from dictionary to a JSON file. There is, so we can calculate tanh-motor coefficients and compare the molecules by the tanh-motor, by the tanh-motor similarity. Here we see that on the most phenols with the amino and carboxyl groups differ the most. And expectedly, ortho, para, and meta isomers differ, are very similar. So basically, by using the previously mentioned fingerprints, we analyze the presence of functional groups in a molecule. And we can also perform molecular mechanics optimizations and store the structure of our phenols as mol files. Basically, so I perform optimization and write mol files. So here, yes, SDF stands gives us basically the files we have discussed previously. So basically, we have a mol file that can be visualized. So it's a methylated phenol. And here, for example, we can have phenol with CF3 group in the second position. So this is all for today. Thank you.